Hello everyone, Tony here. In this video, I want to talk a bit about computer networks, and in particular about how Ethernet hubs and switches work, and how switches actually keep track of MAC addresses of the connected devices. So while I haven't done a full video on explaining the OSI layers or anything, this is an interesting point because I got to see a building's network hub room and they were still using Ethernet hubs. And at first, I want to talk about the difference between Ethernet hubs and switches and why hubs have pretty much gone extinct in any modern install and being changed out for Ethernet switches. And second, I want to talk about once we know about how switches work, I want to talk about how they actually keep track of the devices that are connected and where packets should be routed. So let's get started with the simpler one, Ethernet hubs. So most of you probably know that Ethernet, in its classic implementation, is based on a bus architecture. This would be something like I have one shared communication line, and we can have, for example, computer A, computer B, computer C, D, so on. And this is essentially how an Ethernet hub works. While a hub will have multiple ports, so let's say I had a 4-port Ethernet hub here with 4 ports are usually very uncommon. Usually people will do like 5, so you can like 1 uplink and 4 downlink. Technically, on an unmanaged switch, the uplinks and downlinks don't necessarily matter. Oh, and also I'm not going to talk about managed switches in this network. That's kind of out of the scope of this video, but maybe we'll do another video on that at some point. So we have 4 separate wires, but internally, an Ethernet hub maintains the bus topology. So this is a very classic textbook explanation of a bus. Basically, everything is sharing the same communication medium. And what this means is that A cannot be talking at the same time in B, or C, or D. If any one of these is sending a packet, so let's use blue here to represent the packet. Say computer D wants to send this packet onto the network. This packet is actually going to travel everywhere along this wire. And by the time it gets to B, if B also decided that it wanted to send a packet, well, then we have a problem, because that's how network collisions occur. And we have algorithms that can kind of help detect and prevent this, something like CSMA-CD or CA, to take care of collision detection or collision avoidance. Usually in typical wired networks, you will do collision detection. And if you detect that a collision has occurred, wait some random amount of time and resend the packet. How many times can it possibly interfere with each other? So we'll just repeat that on loop until eventually it works. Or you hit the maximum number of retries and the packet gets dropped. And hopefully you're using something like TCP that can detect when packets have been dropped and resend it. Essentially, the core idea of this is that there is one collision domain, since everything's on the same bus, which means that all of these can have collisions with each other. Nothing should be ever speaking at the same time, otherwise problems will occur. And you might say, well, this looks like one wire, right? So this would be like a very naive implementation if you literally just spliced 4 computers into the same wire, which doesn't typically happen. But the way it would look in this diagram is on my hub here, so this is our hub, we have 4 wires that are going into the hub. So I've just drawn it in a bigger fashion. And all of these inside the hub are technically still on the same medium. So they're kind of all just connected to each other. And so say, instead of computer A, this was router R1, and this was computers A, B, C. If the router wants to talk to computer A, it's actually going to send a packet that goes to all computers, and these 2 computers just have to be like, oh yeah, that's not for me, let's just ignore it. And similarly, if B wants to talk to the router, it can't just talk to the router, it sends a packet to everyone, and the router just has to be like, oh yeah, that's mine, and hope that C and A and no 2 devices decided to send their packets out at the same time, which would be a collision. All right, so this is a very classic bus. That's how hubs work, and this is kind of why hubs started to go extinct, right? With 4 ports, you might be like, oh yeah, well, what's the problem? What are the chances 2 people click at the same time? And if they do, it's probably just going to work itself out. With 4 ports, it might be fine, but what happens when you're on a building and the ISP is cheap, and so they're using 24-port Ethernet hubs? I mean, it kind of will become a problem at some point. And so this is why the big switch has happened from, the nice pun, from Ethernet hubs, so this being how a hub would work, over to a switch. And I'll just draw that for comparison on this side. So physically, they look the same. Again, we just have our box, and I'm going to assume that we have a 4-port switch, just for simplicity. Again, typically switches will be 5 or 8, 16 ports, and again, why 5? So you can have 1 uplink, 1 going to a router and 4 computers connected to it. Typically, what we call going to the router is the uplink, and the other devices will be the downlink, but unmanaged switches don't really care, right? So here's how a switch works. A switch is actually based on, unlike the bus, it's actually a serial implementation. So we have 4 separate lines, but they either go to a dedicated chip that's controlled by a CPU. So say we have like some, usually I say dedicated chip because generally switches tend to be implemented with ASICs, application-specific computers. Just because there's a lot of like 400 megabit, you're fine, but like as we go faster and faster, at some point you don't want to run everything through a CPU. So here we have like, say we have a CPU. Again, could be a CPU, could just be a generic ASIC. Managed switches will almost always have CPUs. If for like nothing else, just do like the management. And let's say we had the same example, right? We got router R1, and here say we have computers A, B, and C. So the way a switch works is if router R1 wants to talk to A, well, first of all, what you need to know about networks is that, so we said that we have, I guess we should talk a little bit about OSI layers. Hopefully I have the battery life for that. All right. So the first layer is physical, right? And that literally refers to the wires that are carrying the packets. Now, one layer above physical is L2. This is called the link layer. And the link layer is concerned with like the next hop. Where is this packet going to go next? It doesn't care where it's trying to go at the end. It doesn't like care about the final destination. That's what like the third layer is going to be for. The second layer cares about where do I go from here? Like what should on this network with this router, what's my end node? Am I going to another router? So say a packet's getting carried across the public internet. There's tons and tons of these routers. So your packets may be going to go from here over to this other router. Or if we're inside of a LAN environment, so like everything's in here, say I'm sending a packet from my computer, well, the next hop is going to be the router or the gateway because that's what's going to like send it off to wherever it's going afterwards. So that's a link layer. Link layers use MAC addresses, which are like the hard-coded or burned-in addresses onto the switch. Yes, you can emulate them, whatever. This isn't about MAC address spoofing. We have the MAC address, and so that's how it knows. For example, if router R1 wants to send a packet to A, it's actually going to use the MAC address. The same thing happens here, right? If router R1 wanted to talk to A, it uses the MAC address. And that's how it gets sent to the hub, and it goes everywhere. And the computer knows, hey, is this my MAC address or is this someone else's? If A knows what its MAC address is, obviously. And if it's like, oh, okay, cool, this packet's not for me, it can ignore it. If it sees that, oh, the destination MAC is for me, take note of that, right? Like, that's obviously something coming to me. So like, in that regard, they're basically very similar. Now, packets don't travel the public internet with MAC addresses. We use IP addresses. So that's where L3 comes in. L3 is the internet protocol layer. And these use IP addresses like IPv4 or IPv6. If you are the largest Canadian ISP, you realize that the year is 2022 and you still don't care, so you still use IPv4. If you're maybe sensible, you realize that, hey, we're almost out of IPv4 addresses, and how about instead of what like IPv4 guys are doing, where they just double NAT everyone and put the entire like apartment on one public IP and then give you private IPs within private IPs, resulting in double NATs, which is network address translation. We can implement IPv6. Anyway, this isn't a rant about Canadian ISPs. All right, so we have IPv4 or IPv6. Doesn't like whatever. For the example of this, I'm just going to use IPv4 because it's easier to demonstrate. But they're pretty much the same. And L4 is then the transport. And so this will be UDP or TCP. And L5 is application. Okay, well, this is the IP layers. Like technically the OSI layers, there's like more of them, but like they're basically the same thing. So like, let's just stick with the simpler example. MAC is where I want to go on my next hop. The IP is where I want to go at the end, like on the public internet, and the transport to where I want to go within that computer. So UDP and TCP both implement port numbers, ports 1 through 65535 that you have probably heard of, and that will make sure that you end up at the right like session. All right, anyway, and then finally application, that's something like HTTP. HTTP could be FTP, IRC, whatever. All right, so within this, let's just look at the first 3 layers, because that's all we're going to be concerned with here with the router and whatnot. Transport, great, but like that's for another video. So say the router got like a packet from so the router maybe has like a different connection here to like ISP or something, which realistically is just made up of a bunch of other routers. So say you have a packet coming into you from the public internet. We have to make a distinction here. If the network is using NAT versus if it's not using that, if this is something like a household where you only have one public IP address and all of these devices only get private IP addresses, let's just assume that this is something like an office where everyone gets a public IP, okay? So when something's coming in, it already knows that, oh, hey, I'm going to like computer A or B or C. Let's assume that, because otherwise we technically have to know that like either you need to port forward here for if there's an incoming packet, or the incoming packet will be a reply to a packet that one of these devices sent out, in which case it would be replying to the port. And the way NAT works is basically it'll give you a specific port mapping between the internal network and the external network. For example, like port 80 can translate to something. It'll just use whatever ports it wants, and then it'll convert those anyway. So like incoming would go to the router, which does that anyway, but that means that the router is technically L4 and it's not an L3 router. Let's assume this is an L3 router, and let's assume things have like IPv4 normal addresses, and it's like on the public internet. So packets coming in, and say this packet is trying to go to computer A, right? So it gets here and it knows, okay, so like it's gonna go to A. But how does it actually know which of the local computers it is, right? So on the router, we could maybe you just have a very fancy router, right? And like your router has one interface for each computer. But this is not typical, right? In a typical situation, your router would have like maybe a WAN and a LAN interface if it's like a home, or you'll have like 2, 3 interfaces, just to like, because the router just has to connect multiple networks together. And within a network, you'll use switches because they're a lot cheaper, and it'll do everything you need in this case. So we have to use what's called ARP. ARP is Address Resolution Protocol. So I'll just add that in here in blue. What ARP will do is essentially, it's a protocol where I can give it an IP address of the device I'm trying to get to. And it works both in public and private IP addresses. But so the router doesn't know, like it has given IP addresses to these, and things like they know what each other's IP address is. So this, like the router knows, oh hey, this is that IP address. So say this is, if this was internal, maybe it's a 10.0.0.2. This interface is, say, like, I don't know, your ISP uses the 172.16.0.2 or something, 10, and then say this network has IP address 10.0.0.1, 10.0.0.3. When I say 10.0, I mean 10.0.0.3. So this is, for example, would be standard for like a class A network. So anything 10.0.0.0/8 is reserved for internal private use. A lot of ISPs sometimes do use something like 172. 172.16.0.0, I think, /12, I want to say, is open for private internal use. And then 192.168.0.0/16 is open for private use as well. So this is, let's say, 10.0.0.4. All right. A is going to 10.0. Well, actually, it doesn't know it's going to A yet, right? So there's an incoming packet. And let's just assume again that there's no NAT. So for some reason, something out here knows the private IP addresses. So maybe not the most realistic option, but like a router will like perfectly happily switch networks. So let's say we have a packet coming for 10.0.0.2. Is this too small? Okay, well, I'm writing a little small, and unfortunately, this camera is only 540p. It doesn't support full HD. So maybe it's going to be a little hard to read, but hopefully you guys can still make out what I'm writing here. So this is going to 10.0.0.2. Now the router needs to figure out, all right, like it knows that the way the routing table would work is which addresses are on which port. So it knows that 10.0.0.anything, for example. So say 10.0.0.0/8, or so maybe it's a /16 network. Yeah, you wouldn't do a /8. You would because you usually keep the first decimal available to for your subnets. So you would use 10.0.0/16. So the router knows that anything on this port is say 10.0.0.1, and and then it knows that if the routing table says if it's going to 10.0.0.0/16, it has to send it over to, say this is interface 2, I2, and this is interface 1, call it I1. On Linux, this would be ETH0, ETH1, ETH2. So say this is ETH1 and ETH2, for example. So it knows that, hey, 10.0.0.2, that matches what interface, the IP addresses that I should be forwarding to this. And we can talk about how it builds that table with OSPF or RIP, but that'll be for some other video, mostly because I'm already running low on my laptop's battery here. So it knows that this packet's going to have to leave from here. So the router will say, all right, let's forward it. But also, the router at this point needs to figure out who the end target is. So it needs to figure out who has that IP address. So we know, like we're looking at this from the bird's eye view, right? We have more information in the router. We know these numbers. We know that C is 10.0.0.4, B is 10.0.0.3, A is 10.0.0.2. Maybe the router knows that these numbers exist. Maybe it doesn't. So the router actually needs to figure out what is the physical A, B, or C. Like what computer does this IP address like translate to? And that's what ARP will do. So with ARP, you give it a IPv4 address or IPv6. So in this case, the router is going to perform ARP on 10.0.0.2. So the way ARP works is it's going to basically send a broadcast. Now, what's a broadcast? A broadcast is essentially just means it's going to send to everyone on the network. So the router is going to send something to MAC address, usually depending on what your broadcast is set up. But each network will have a broadcast address and like a local routers, gateway default IP. And there's also a broadcast MAC address. And the broadcast MAC address is all Fs, F, all the way. And so if you send something to that MAC address, everything knows that, oh, hey, this is a broadcast. So it forwards to every other device on the network. So it'll go everywhere. So the router is going to send a broadcast asking who has the IP address 10.0.0.2. And that's going to go over to the switch, and the switch is going to be like, oh, that's a broadcast. We need to make sure everyone gets this so that they can reply. And so unfortunately, I don't have a different color, so maybe I'll just do it in black again. So the ARP packet is going to all FFs. I'll just write FF because I don't want to write out all the bits. And so the switch gets it, and the switch says, all right, we need to send it out to everyone. So who is that going to get sent to? That's going to send on all three of these channels to A, B, and C. So each one of A, B, and C received this ARP request. And basically it says, hey, do you have this IP address? And in this case, B and C are like, no, that's not us. So just don't do anything. A is going to be like, hey, that's me. I have that IP address. So A is going to send a reply. We know that A has that IP. So A is going to reply saying, hey, I have this IP address over. It's going to then make its way to the switch, and the switch is going to send that back to the router. But, so let's say A's MAC address is 1, 2, 3, 4, 5, 6, ... right? So again, very, very unique and creative here. If this was on the hub, it would be the same thing, by the way. So the router gets the packet, and say the router's second interface was there. And since it's on a bus, everyone gets the broadcast anyway, because everything on a collision domain is essentially a broadcast. And A would then reply. So that's fine. But the thing is here, so once A replies, right? And once the router knows the MAC address of A, it can be like, oh, cool, okay, here is your new layer 2 packet with A's MAC address as a destination. So let's skip the switch part, and let's say so A sent it, and it's gone back to the router, and so now the router knows the MAC address of A. It knows that, hey, this packet that's coming here, I've received this, I've dealt with it, I know that I'm actually going to send it not to that IP address, because that's global. It knows the next hop is going to be to MAC address 1, 2, 3, 4, 5, 6. So the router has saved this, and here comes the new packet, right? The router is going to send the new packet off, and it's actually going to, so the L2, the outer packet is going to 1, 2, 3, 4, 5, 6, ... and so the MAC is, the outer is here, and the inner is here. The inner is going to 10.0.0.2. because the L2 packet encapsulates the L3 inside of it. All right, and then magically the switch knows which port A is on. And that's the part I wanted to actually discuss in this video before I went on a 24-minute tangent. And so then it's going to make its way off here, and it's going to come. And A will receive it, and it's like, oh, hey, that's my MAC address. So it'll decapsulate it, and once it decapsulates it, it'll see, hey, it's for IP address 10.0.0.2. Decapsulate it, it'll give you the L4 transport protocol, and then TCP will be like, okay, cool, this is going to port, I don't know, 80 for HTTP, for example, or 443 for HTTPS, or 22 for SSH, whatever. Say it's like an HTTP packet, and so it'll forward it to whatever application that is, like Apache or Nginx or whatever is going to deal with it. But that's the rough flow. But the one part that I have skipped in all of this is how the heck did the switch know where A is? On this one, on the hub, it's really easy. When the router finds out that A has MAC address 1, 2, 3, 4, 5, 6, It just sends it with MAC address 1, 2, 3, 4, 5, 6. And since everything's like on the same internal network, like it's on one like bus, it's that like when R1 here actually sends, say it sent that same packet going to 1, 2, 3, 4, 5, 6. Of course, MAC addresses are longer than that. So that's my outer L2 packet, and my inner, yes, technically they're not all called packets. There's packets and datagrams, and I'm simplifying it here. And the inner, once it decapsulates it, is 10, 0, 0, 2. That's going to make its way here, which means that it's going to actually go to every single one of these. And all of C, B, and A are going to check, hey, is that my MAC address? Nope, so this one gets dropped, this one gets dropped, and A will naturally get it, and it'll be able to read the packet and do whatever it was going to do with it. And that's just because there's no logic. Like any packet sent, as I said, the whole point of the bus is anything sent goes to everyone on that bus. That's how a bus architecture works. But here, we're not using a bus architecture, right? We're a little bit smarter. So how does it work in this case? Well, essentially, a switch has to be smarter than a hub, and the switch has to keep track of the MAC addresses of like the packets that are flowing in and out, and it has to keep track of who is connected to it and with what MAC address. So hopefully I have enough space over here. The way this works is that the switch has a port and MAC table. Actually, typically this would be the other way because it's going to use the MAC addresses for lookups. So the key is the MAC and the value is the port, but actually it doesn't really make much of a difference just for like my demonstration. Of course, it makes a difference when you're programming it, and I should clarify that this is a physical port number, not like a TCP or UDP port number. So it's like an interface. So let's say this is 1, 2, 3, and 4 on the switch. So when router R1 sent the first ARP request, right? Because router R1 needed to know the MAC address of computer A. So the router sent an ARP packet. So the address resolution protocol meant that the router sent its MAC address, just so that the device knows who it's going to reply to destination FFFF. So in the ARP, the source was the router's MAC address, and the destination was everyone, FFFF, the broadcast. And so when the switch saw this, let's say the router's MAC address was, or let's just call it ABCDEF, because they're hexadecimal usually. So the switch saw this, and it's like, oh, hey, look, ABCDEF, that device with that MAC address is connected to port number 1. So it now knows, and usually these tables will be kept in memory. Most switches, I think, can store a couple hundred or a couple thousand of these MAC addresses in a small table, just kept in like local RAM. And they'll keep it for some predetermined or pre-specified duration. I apologize that this table is very small. That's what's going to be kept in memory. And so now the switch knows that, hey, when A sends a reply, and A's reply is going to ABCDEF because it's going back to the router to tell the router, hey, I have that IP address. The switch knows who it's going to send it to. It doesn't have to send it to all 4 because it knows where it is. Now, what happens if the switch doesn't know who it's going to? I'll get to that in a minute. But basically, when A then sent a reply, A's reply had A's MAC address. So what happened here? Oops. And I just painted on my t-shirt with the marker. A sent a reply from 1, 2, 3, 4, 5, 6. And so the switch now knows, and it has learned what A is on. So there you go. That's how the switch knows. And so when the router went to send this packet with 1, 2, 3, 4, 5, 6, and it went to the switch doesn't have to send it to all 4 of these. Because if it did, it's basically acting like a hub at that point, right? The switch has its own separate collision domain. So it knows, oh, I know which port number this MAC address is connected to. It's connected to port 2. So that packet is only sent on port 2, and it makes its way to computer A. And this is very elegant because this is completely transparent to the end user. They're at no point on an unmanaged switch did someone have to tell it what things are connected to. Unlike a router and giving IP addresses, there's no DHCP. It's surprisingly simple. It's completely passive. As packets flow through it, it will learn what ports they're on. And once it knows where something is plugged into and which port it's on, by port I mean the physical port. So say on this physical device, this is port 1, 2, 3, 4. I'm not referring to port numbers in TCP or UDP. Yeah, once it knows the 1, 2, 3, 4 and like what port it's on, it now can just send the packet straight to that port. It doesn't have to send to all 4. Now, what happens if the switch doesn't know, right? Say the router decided to send, so let's get rid of this example. And let's say, again, this is something we know. Let's say C had port number 4321FE or something, all right? Say magically the router got an incoming packet that was going to 4, and it knew what this was. Say the router had done ARP earlier, and it kept it in memory, and it knows what 4321 is. So here's my new packet, and it's going to 4321FE on the outer, and the inner L3 packet is going to 10,004. Now, again, the router is smarter and it has way more memory. So there's a very good chance that the router already knew what like 4321FE is. But maybe the switch only keeps MAC addresses in its table for an hour, maybe 2 hours, maybe 12 hours, maybe 24 hours. Either way, at some point, if it hasn't seen this device in some amount of time, the switch is going to erase this line from the table, right? So say maybe 4321FE was here on port number 4. But maybe it hadn't spoken in a little bit, so the switch forgot it and it got erased off of the table. And you might ask, like, why does it have to erase it off the table? Like, the network hasn't changed. But again, if you're not sending packets, the switch doesn't know if it has changed. Like, maybe the port's still connected, but maybe I unplugged someone's desktop computer and I plugged in my laptop. Or I left and my friend came in and my friend plugged his laptop in. Like, each one of those laptops is going to have a different MAC address. It has to eventually make space in its table, and it's going to get rid of things. And by the way, a switch can keep track of multiple MAC addresses. Now you might say, well, technically, aren't there like infinite MAC addresses, right? Like there's a bajillion public devices on the internet. How can the switch the switch is going to keep track of everything and know what's on port 1? And the answer is no, because as I said, the MAC address is only for the local, like it's for the next hop. So it only has to know the MAC address of the router. Any MAC address past the router, the switch doesn't give two hoots about. It doesn't care, because anything going from A, B, or C is going to go to the gateway first, which is the router. So it only has to know the MAC address of this. It doesn't have to know the MAC address of anything past this. That's basically for the router, because the router implements, of course, it implements like the first layer physical with ports, but it also implements L2 and L3. So the router will figure out the MAC address of the next hop it's going to go to, and it's going to figure it out by using like ARP and whatnot. Again, separate discussion. So over here, 4321FE went to the switch. The switch doesn't know what it is. So what does the switch do? Well, it's going to send it to all 4. The switch cannot make ARP requests arbitrarily, because a switch does not implement layer 3. So the switch doesn't know, and nor does it care what the IP address of this is. It never decapsulates the L3 from the L2 packet. So it's basically just going to look at the MAC address and the MAC address only. And if it doesn't know it, well, it has a fallback. Act like a hub. And so what the switch will do is, if it has never seen this before, it's going to send to 2, 3, and 4. So every single one of A, B, and C are going to get this packet. And again, this might be a little bit inefficient, but this happens rarely, right? So say eventually it gets it, C gets this packet, and A and B know that, hey, that's not my MAC address, so let's ignore it. C gets it, C's like, oh, hey, yeah, that's coming to me. And eventually, sooner or later, so far the switch doesn't know. The switch doesn't know that A and B have dropped this, and only C is like, yeah, that's for me. The switch has no idea about that. But sooner or later, device C is going to send a reply, right? Like if someone's speaking to C, it's not going to ignore them forever, unless it's UDP, in which case you can't completely ignore it. But if it's like TCP, it's going to send a reply. And so if it's something like TCP, TCP will send ACKs, right? Acknowledgements. And again, we can talk about TCP Reno versus TCP Tahoe, and how often acknowledgements are sent in each, and how that whole protocol works. But if you want to see that, leave a comment down below. I'll cover it another day before, after I charge my laptop. And so eventually C receives it. C has a reply, and the reply from C is going to go to the IP address of whoever sent it, right? So say I've only been writing the destination MAC address and IP address in these example packets here, but each packet, like each layer, has both the source and the destination, right? So L2 has the MAC of the source and the MAC of the destination. Similarly, L3 has the IP address of the source and the IP address of the destination. This is literally for like the same thing as the postal system, right? If you send someone with a source, like a destination, but not a source, C gets it, and it's like, well, that's great. Who do I even reply to? Like, it won't know where like it's supposed to send a packet back to. So there's always the source. So once C gets it, it knows that, hey, it's actually computer, say it's say this packet came from 172.16.0.3 or something, right? Maybe that's the IP address of Google. Maybe it came from 8.8.8. Maybe it came from Cloudflare, 1111, whatever. That's an easy example. See, like when the packet came to it, it know what the source is, and it's probably going to keep track of it. In fact, TCP is going to keep track of not only the source IP address, it's going to keep track of the source IP, destination IP, source port number, and destination port number. UDP, on the other hand, will only keep track of the port numbers. So this is going to now send a reply off to 172.16.0.3. And eventually, this reply, so let's get rid of these arrows, because like those packets have already been dropped. So the reply makes its way over to the switch. And this is where it's like, bingo, the switch now knows who 4321FE is. And it's like, hey, that device is on port 4. Because when this is getting sent, this can be the IP. And let's say the destination MAC is now the router, right? So it's AB. Because when the packet was coming here, the source IP address, again, IP address is out like beyond this network. It's the whole internet. It's where you're trying to go at the end. Like, it's my final destination. It's a computer I'm trying to get to. Not where in the computer. That's the port number. That's for TCP and UDP. But which computer I'm trying to get to. And the router, when it sent it, will have put its MAC address into the source. Because that's now that's a local network. When it comes back, it's telling the computer, hey, your next hop, when you send like a reply to this, should be me, because I'm the one that's going to send it like past that. MAC address, so basically that was the source MAC and IP into this. And C now is sending the reply. So C's destination is the source it first got. So the destination MAC is the router, because that's the first hop. And the destination IP is who sent the packet. So like that's somewhere out on the ISP network. It's somewhere out here. And in fact, this is going to make its way to the router. And actually, we'll talk about what happens there. So anyway, this packet goes to the switch. And the switch will read the source MAC address. Just like how when the router had sent the packet, it read the source MAC address, and it labeled, hey, you belong to this port number. Now that this is sending it, it sees a source MAC address, and it knows where it's coming from. It just says, hey, I just had a packet coming on port 4, and it had this MAC address. Let's save that. Let's like note that down. Let's save it over here. So it does. It's going to save it as here's what's connected on port 4. And then it's like, well, what's the destination? Do I have to send it to everyone? No, because it knows it had the MAC address of the router saved. So it knows ABCDEF is on port 1. So it only sends it here. Now, what if, say, this switch had forgotten this? Like enough time had passed and it had erased this row. It didn't know like which port number this was on. Well, in that case, as happened when it was getting this, it would just send it to all 4. It would act like a hub. It would send this packet to all 4 interfaces until it got a reply from the router, like until it knew what the source was, and it could add it again. But in this case, let's say it has it, so it adds it. So it's going to make its way only to here. Again, if this row wasn't here, it would go to all 3 ports. Since it is here, it knows that it has to only send it to this one. So it only sends it to that one. It comes to the router. Now the router decapsulates it, because the router is L3, so it's going to read all the way to the L3 packet. And the router sees that, hey, this packet is trying to go to 172.16.0.3. And it's going to look at its routing table, and it's going to say, which way, so how do I go to 172.16.0.3? So that's like the equivalent of like, hey, let's read the road sign now. Like, am I going to Montreal or am I going to like Waterloo, right? Say you're in the GTA. It's like, yeah, am I going to go like east or am I going to go west, basically? Which way am I going to go? It's going to read the sign, which is its internal routing table. And its routing table knows that, hey, if it's going to 10.0.0.0/16, that's interface 2. It's going to go on interface 2. Anything else, for example, is going to go to interface 1. Now, of course, this is a very simple router. It only has 2 interfaces. If you're an ISP, your router might have, I don't know, 20, 30 interfaces, right? Say you're like a large ISP and you're in a major city. Well, maybe you have a direct fiber optic link to like the 10 closest cities. And maybe one across the Atlantic, I don't know, like one of the undersea cables. Your routers Every packet that comes in, your router has to be like, which of these 30 outputs am I going to send it to? Because it's not like there's one input and outputs, right? It can come from A and go to B, and it can come from B and go to A. Like routers are bidirectional. Hopefully we're clear on that. The routing, that's what the routing algorithm will do. It'll figure out, and usually there will be some cost associated with the path, right? So the router knows. Like in this case, there's only one way it can go, so it's very simple. It's going to go here. But if this was something we're doing at the ISP level, well, maybe I have a main 10 gigabit, 100 gigabit fiber optic link that goes to that city. But maybe I also have a copper link, like as my backup, or it's like the express versus slow way. Like obviously, you're gonna have a cost associated with it. If the fast way is available, send it along the fiber line. Why would you send it on the copper cable? But what if the fiber cable gets cut up because some guy in a excavator decided to rip up the fiber optic cables? Well, then the router has to know, okay, well now the cost of the fiber link is infinity, so I got to send it along the copper way. This is similar to, for example, how companies like Google or OVH or DigitalOcean or any of these big internet firms will do peering, right? So in a peering facility, basically, your ISP has to decide, okay, we know that this packet is going to my OVH server, right? Am I going to send it A to the fiber optic cable that goes to the OVH Beauharnois data center? Or B, am I going to send it to my ISP's router in Montreal? And then it's obviously there's a cost. If you can go direct in a peering facility, obviously it's way faster to go within the peering facility and do an internal route and go straight to that provider. Maybe you're watching Netflix, maybe you're watching YouTube on Google, right? If it can, obviously sending the packet straight to YouTube or Google is a lot better and a lot faster. So that's what it's going to do. But maybe, back cable's congested or something, then it can take the general route. Maybe it's going to go to the next hop, which then goes to the next hop, or however the ISP has things considered. That's all for the ISP. Anyway, that's beyond the scope of this video. We can do a video on routing algorithms, as I said. So it comes here, and the router is going to look some way it's going to figure out which interface it should send it to. And if this is a household router and it only has a WAN and a LAN, it's going to send it to the WAN port. And there we go. And it's happily ever after, right? And now the switch has learned this. And this is how the self-learning switches work. Completely transparent. If it doesn't know, it sends it to everyone. If it does know, and the way it learns is when it gets something coming into it, it snoops on, wait, who sent this to me? Who sent this, right? And by the way, switches don't have MAC addresses on their interfaces. This is why I mean they're completely transparent. C doesn't even know there's a switch here. As far as C is concerned, it's plugged in straight to the router. As far as A is concerned, A is plugged in straight to the router, right? It's completely transparent. So this entire learning thing happens transparently, but also none of these interfaces have MAC addresses. The interfaces on a router do have MAC addresses. So C knows that, hey, I'm trying to send this to interface 2 of router 1. But it doesn't care. If this was a router up here, I don't know why you'd use a router up here, but say it was a router up here. The MAC address of this would have had to be the interface on the router, and the router then decapsulates, puts the MAC address of this port and the MAC address of the next one, and it would have to send it. They'd have to you'd have to read and shift over your MAC addresses each time. And that would actually be multiple because each interface on the router would have a different MAC address. In this case, we know that's not going to happen. It's a lot simpler. You don't care about the MAC address on the switch side at all. And so yeah, there we go. That's the fully worked out example of how learning switches work and how the packets are routed along the internet. So I just realized after filming that video that I forgot one of the cases, and that is that if, by the way, the switch happened to be connected to, say, another switch, it can actually keep track of multiple MAC addresses per port. If this was my switch again, and this port of it happened to have computer A, B, C, and any number of computers, that's perfectly fine, because what the switch can actually do is it can, in that table that I was showing you, with the MAC and the port number, it can actually keep track of the MAC of A, B, C, and say these are all on port 4, that's perfectly fine. The switch can write all of those. And so what happens in this case is if something's going to any one of these MAC addresses, in any of those 3 cases, it'll go to port number 4. If it's going to a MAC address it's never seen, again, it goes to all the ports. But if it's MAC of A or MAC of B or MAC of C, it knows that, oh, hey, these are all on port number 4, so send it on port 4. Now, this could be for a number of reasons. Maybe these are just connected in a single collision domain, just like a hub. In that case, yeah, it's gonna, when this is sent over here, it's gonna go to both A, B, and C. And it's up to A, B, and C to know to ignore it. Or maybe this is just the case that this is quite common. Maybe there's just another switch down here. So say this is the switch in the basement of the building that like routes it to each of like the units or suites. And within the suite, we have a switch. And our switch happens to have A, B, C connected this way. Now, because switches are transparent, according to this switch, A, B, and C are all here on port 4. But actually, they're not. Because basically, this switch will send anything with MAC of A, MAC of B, or MAC of C down this port. And when this switch gets it, this switch, so this is here, this has its MAC and number table. And this one knows that, hey, A is actually on 1, B is on 2, C is on 3, if these are labeled 1, 2, 3. So this switch doesn't care. It's transparent. It sends any one of those down to here. This switch knows, hey, A, B, and C, and it will know which of these to send it to. So hopefully this clarifies what happens if you daisy chain switches or if you have multiple computers on one port. It just works. That's all for the follow-up. Back to the original video. All right, that's all I have for you today. This video has gone on for over 50 minutes. I'm going to cut it here, mostly because the laptop I'm recording this on is about to run out of battery. Thank you all so much for watching this video. I hope you learned something. I hope you learned something about how networks and switches work. Maybe if you're in a like unmanaged switch in your house, this has given you some insight into how that works and how they interact with routers, and even how packets are routed across a local network and what the difference between a switch and the hub is. Networks, computer networks and networking is one of those topics where I hadn't had the confidence to make videos about it before. And I still don't have much of the confidence. So this is kind of like a test. I guess the same thing happened with like me teasing, like trying the files and like compression type stuff with the zip versus tar GZ and the Linux stuff with the Linux audio explained video. If you learned something from this and you enjoyed this video, please consider leaving a like or subscribing to my channel. It helps me out a lot. If you have any suggestions for future videos, feel free to leave it in the comments. Or, as I said, I hope you learned something. I hope you found this interesting, and maybe it's given you, some insight into computer networks. Thank you so much for watching, and I will see you all next time. Bye.